Okay, this is the second video experiment in the overall experiment on the transference of electric power, the comparison between a 30-metre single wire and the Telluric transmission medium. So we've already done the experiment with the single wire, 30-metre single wire, and the best efficiency that we were able to get so far in that experiment was around about 40% at about 1.89 megacycles. So in this experiment we're going to use the same apparatus, the same cylindrical Tesla coils set up in the same way in the first lab, and the receiver is set up in the second lab. The point-to-point distance between the RF ground system is about 18 meters between the two labs, and as I mentioned previously earlier, the ground system is connected by this very thick 0 AWG microstranded silicone coated wire down to the specialized ground system, and I'll be showing you that shortly in this video. And at the other end then we also have an RF ground system, or a ground rod, which uses the same cable in order to connect the ground system to the receiver coil. Otherwise the generator is the same. I wanted to do a comparison of the two transmission methods, and therefore I haven't changed anything about the setup, and the setup is also the same at the receiver. So the first stage here was to get everything to a tuned starting point, and that involves setting up the transmitter. Now that they are not coupled by a single wire, the transmitter can't see the receiver, so if you were to take a small signal AC input impedance measurement Z11, as I normally do with the DGA SAQ network analyzer, then at 30 meters you can see the receiver down the wire in the transmitter, and that conveniently allows you to match the two resonant frequencies of the transmitter and receiver coils. That's not the case when using a transmission through the ground. So I need to set each one up individually, and to do that I connected the network analyzer to the primary circuit of the transmitter coil, and we have the bottom end connected to the RF ground as already said, and the top end we have that adjustable telescopic aerial that allows us to change the wire length at the top end of the secondary coil, and that allows us to do fine tuning of the frequency. So I've done that. I'll pan the camera around so we can just see the measurements. There's the computer. I'll just zoom in on that a little bit. I'll put these detailed measurements in the write-up, but it shows that it's a typical single Tesla coil result. The series resonant mode, that's where we get the phase change, and the minimum impedance of the coil is at 1.87 megacycles. That was the closest tuning that I could get to the best point of efficiency when we use the single wire. And then I use the tuning capacitor in the primary circuit in the normal way to balance the parallel modes, and we can see those at points 2 and 3. The lower parallel mode is at 1.62 megacycles, and the upper parallel mode is at 2.24 megacycles. So with that balanced so I've set the series resonant mode and I've balanced the parallel modes, and I'm going to do the same with the receiver as well. So I'm going to use the camera up in the other lab and then set the same characteristics at the other end.
Okay, I'm now up at the other lab with the receiver. We have the ground system connected here to the lower bottom end of the secondary coil for the receiver. We're still going through at the moment the same power meter, and we still have currently the same load connected. I've connected the vector network analyzer into the primary, and we still have the tuning capacitor connected. So what we're going to do is we're going to match this system. We're going to set it to the same frequency as the transmitter. So we set the frequency using the VNWA to 1.87 megacycles. And I've done the same here, so I've adjusted the length of the telescopic aerial until I've arranged this. Just zoom, although this won't necessarily come out, but I'll show the traces in the write-up. The marker 1 here at the fundamental series mode for the receiver is at 1.87 megacycles. So that sets our cylindrical transmitter coil and our cylindrical receiver coil at nominally the same series resonant mode at 1.87 megacycles. I've also balanced the parallel modes using the tuning capacitor, the vacuum variable capacitor in the primary circuit acting as the tank, so that the magnitude of those two split parallel modes are balanced. And that is the starting point, so we know that the two coils are set up on the same basis.
Okay, so I've repositioned the camera outside of the first laboratory where the transmitter is, so that we can have a look at the dedicated RF ground system, which is built for the transmitter for the Telluric experiments. And we can see that this is a system constructed from 22mm copper pipe. Each of the pipes has been driven down into the ground. There are 11 on the main section, and then there is one separated at the top section. I'll explain why that is. But there are 11 22mm copper pipes driven at least 1.5 meters down into the ground, and they have some holes at the sides of those pipes as well, and then connected across the top again with all brazed together with copper pipe to form one complete unit. Now ideally I would prefer to have this in a star configuration with a central point, but that's obviously often shown to have the best impedance performance, especially at higher frequency, where you have the radials all coming out from a central point. This is as much space as is available, so the best way to get as much copper into the ground here was to have a straight section going from the bottom all the way up to the top, with 11 vertical sections down into the ground. Now, because this is made with copper water pipe for a reason, it has water inlets at the bottom and the top, and that allows you can connect a pipe, a hose lock pipe onto there, and you can actually run water into the system. So when you run water there, it runs down the vertical pipes and gradually fills up from the bottom to the top and soaks away into the soil. And that's also the point of having some of the holes in the tubes that are driven into the ground. So that gives the advantage of being able to reduce or minimise the impedance of this ground system by pumping water in, and it makes a significant difference. So if you leave this irrigating for about an hour, you're going to reduce the impedance, the input impedance of this Z11 by at least 10 ohms, and you can get this system down along with the joining wire, which, as I already said before, was a 0 AWG, so it's quite chunky, but it's microstranded wire, suitable for an RF ground and silicone coated. You can get that whole system down to about 10 ohms at the frequencies that we're working at here, and if the ground is tuned, obviously we can even reduce the impedance a little bit on that as well. We have a reference pipe, so the one at the top there, which is single pipe down into the ground, that is as a reference, so we can measure impedance between those two. We can also use it as a reference ground to see what we pick up when we actually put it down into the main system, and that has a smaller reference wire going back into the lab as well. I'll just show how that's all connected up. So I pan the camera around a bit. There's the wires heading into the side of the lab. On the other side of the wall, we're then straight into the transmitter. So that's the dedicated transmit. It's about a reasonable amount of copper that we can get into the ground given the space that we've got, and is relatively, well, not straightforward to build. It was actually quite difficult to put all that down in there, but the advantages of it are clear. Obviously, when Tesla was doing his work on the transmitter and the receiver, he was putting large amounts of copper down at places like Colorado Springs and Wardenclyffe, and we're going to see what kind of impact that makes when we actually go through the series of experiments. Okay, good. I've moved the camera back into the lab, and I've positioned it so that we can see particularly the telescopic aerial at the front of the secondary coil for the transmitter. I'm just going to run the system up as we would be when we're actually doing an experiment, because when we get to higher power, then we will most likely get a small breakout at the top end of that, and that's quite useful because then we can use that to do some very, very accurate tuning based upon large signal tuning versus a small signal tuning. So the small signal AC analysis from the vector network analyzer involves just a very tiny signal, so nominally 0 dBm, or just a single milliwatt of power coming out of the unit, and that's used to analyze the whole system. But obviously when we're running the Tesla coil, we are talking about much higher quantities of power, and the tuning of the system may be slightly different. So the way we do that is we bring the power up. So I have actually set it, I've adjusted this previously, and I've adjusted the 1.87 megacycles of the small signal analysis to 1.86, and I'll show how it is that I did that. So if I bring the power up, it's about 100 watts, 400 watts, to a point where we get a flare at the top. We're putting about 500 watts out, and let's see if that appears. Yes. There we can adjust frequency until that flare is at its maximum. So I go down in frequency, it minimises, go up, again it minimises. I found the optimum maximised flare at the top end there is about 1.86 megacycles. Just lock that into position again. It's about 500 watts. So it's 500 watts of power. Some of it's being dissipated at the top end in that flare. The rest of it is being pumped down through the cavity in the secondary coil and out down into the ground system. And it's that we're going to see how much of that we can actually pass to the receiver. But that is about the optimum position of tune. I'll just wind that back down, fill the lab with ozone. So as a starting point, that is again about the optimum tuning point, and from here we can actually start the experiments. And the experiments start first of all with looking at the difference between what's passing through the ground and what's travelling through the air. I mean, from the transmitted power point of view, this appears like an antenna which is connected to a quite powerful RF generator. So there is inevitably going to be both a sky wave and there's going to be a ground wave. Now the ground wave is what we are most interested in, since we're looking at telluric transference of electric power, but we are going to also need to look at the proportion of that power that's actually travelling through the sky wave as well, as a normal electromagnetic radio wave would do. So in exactly the same way that a normal radio transmitter and receiver would work, we have an antenna. It is obviously somewhat an unusual antenna, being a Tesla coil, but nonetheless it is connected to ground as a transmitter system would be, and it also has a top end aerial in exactly the same way that a normal domestic, broadcast or amateur radio might have. And the same being true of a receiver. The receiver is also a coil with an aerial at the top end for tuning and is connected down to ground. So then we need to make that comparison. And the easiest way we can do that comparison is actually to use a sensitive radio receiver. So I'm using here, just get that in the picture, this is a Sony ICF 2001D. It's from about the 80s and 90s era. It is a mixture of analog and digital components. It is typical of the type of radio scanner from that era, where you could scan over FM, AM, HF band. It covers, well, actually all the way from long wave through low frequency, right down at the tens, hundreds of kilohertz, so 150 kilohertz up to 30 megacycles in the HF band, and it also covers the FM bands as well. So long wave, medium wave, short wave, and up to the FM bands. And what's good about this is it's quite adjustable. So it has things like RF gain, so you can adjust the sensitivity of the receiver. And I've also made in this a modification where we have a B&C input port here, so I can actually choose between whether it comes through the aerial, the normal telescopic aerial, or it can be connected directly to the B&C input. And the B&C input obviously we're going to use to connect to the receiver system. So if I just set, to show how this is going to be useful, if I just put it up on here, it's quite visible. Let me get that in the, yes, that's in the camera. So, and I turn it on. I've got it tuned. Is it possible to see that? Yes, I think so. It is tuned to 1.86 megacycles, so exactly the same as what we're transmitting. And I've got the mode of the transmitter set to CW, or continuous wave. So even with a small amount of power, I've got a relatively large transmitter coil sitting right next to a radio receiver. So I don't need a linear amplifier. I can turn this right down to minimum. We're only going to put out a watt or two of power, and if I turn that on, there immediately we see the reception bar goes always up to maximum, and we can hear the CW tone, that tone being produced by the amateur radio set. Turn it off, and if I adjust the sensitivity, so I've got minimum sensitivity, if I put it up to maximum sensitivity, then I've got the bars right over, hard over from up to signal strength 10. So what we're going to use this for is we're going to run the system, the transmitter here, at very low power, probably no more than about 5 watts, and then I'm going to take this out up to the other lab, and without any connection to the receiver system or in any that way, see the level of signal that I can actually get just over this short distance. So for sure I will be able to pick up a signal, even a small signal. I would expect with this kind of high Q antenna to be able to go a couple of miles away, turn the sensitivity up full, and still just be able to determine a signal, and even at very low power. So that means if to compare what we're getting through the ground, we're going to have to calibrate. First of all, I'm going to need to turn down the sensitivity sufficiently through the air so that I have a defined signal strength, preferably down at 1 or 2. So I know the strength of the signal that's passing through the air between our transmitter and receiver, and then after that I can connect it to the system and look at the signal strength that I'm getting through the Telluric channel, and then I will be able to make a comparison as to the primary transmission mode between the transmitter and the receiver. And then when I've got this set up there, then I will have an assistant at the transmitter that will turn on and off the system, and we see what it is that we receive at the other end. So just before I go up to the other lab with the receiver to do the radio reception experiments with the Sony, I'm just going to do a power test, transfer power directly. So we're using the transmitter into the ground, and we've got the receiver set up, everything's tuned, so we're at 1.86 megacycles. So I'm going to see whether or not we can pass any power along our Telluric transmission medium. So I turn on, I will just check our tuning. Let me bring the linear amplifier on. I also need to reset this as well. Okay, so let's just come up to about 50 watts of power, just tuning. 70 shown on here. Let me just turn this around to check the camera. Yep, 70 on here. Around about 57 there. Obviously there is a difference here because this power unit comes directly out of the linear amplifier, and then the output of this feeds into this manual tuner, and this is on the other side. So this is actually showing the matched impedance at SWR of 1.2. I'm using the manual tuner here to adjust the linear amplifier so that it is tuned through the antenna tuner to the rest of the experiment, and that power meter is in between the linear amplifier and the tuner, so therefore sees the tuned SWR. The situation here is different, so this is in the after the antenna tuner, and here obviously we are seeing the full forward and reflected power. So this is reading 65 watts, this is reading 76. If I look at what's reflected, we've got 17 reflected and we've got 79. So that would, and if I put SWR, no, over its rating at the moment. So this shows us the actual forward power going in, and there is also reflected power coming off of there as well. So there is a reactive component here as well, and that gets tuned out when it comes to the linear amplifier. That's why we have a difference in these two readings. I prefer to keep when running at high power, the linear amplifier tuned as well as possible. I can detune it so that these are the same. Let me just look at detuning that a bit. So there we are, 1.8 SWR, 96 on there, 96 on there as well. So now the linear amplifier is essentially seeing the experiment as it is, without any compensation for forward and reflected power. Bring that back down. .8681 is back where we were before. Okay, so I'm going to wind up in power. 350 watts linear amplifiers, reading 376 here, so actually at higher power, a better match across the whole system with an SW, a nice SW. I've got WR of 1, 355, 320. We look at the other meter, nothing, no power being received. We're not at the point of the breakout yet, 400. Right up to 750 watts, 795 here, again a fairly good match. No breakout at this time, and the receiver is still on 0, no power. So we are pumping out around just over 700 watts of power, pumping that down pejoratively into the ground, but we are still not receiving anything at the other end. Linear amplifier at maximum performance. Can adjust that slightly. Yeah. Let's back this off slightly, a little bit over. There we go. 800, 740, 780, 730. No, quite a lot of power being pumped in. No power being received, like we were on a single wire we were seeing 40%. Now here we're seeing 0%. I mean, we can be sure we'll just use the radio. There is a signal coming out. We'll just turn it on. There, we can hear the signal. Turn it off. Okay, so I've moved the cameras up to the second lab where we're doing the reception, where we have the receivers, and we have the same setup here. We have the ground system connected as before, and I've put the Sony ICF2001D receiver is in the inset picture with a close-up, and that is tuned to 1860. So that's the same as we had set on the transmitter, And this first part, and here we are receiving through the aerial. First of all, we've got to do a calibration to see what we are receiving through the sky wave and what we're receiving through the ground wave. So we don't have the aerial connected here. So we haven't connected the output of the primary. We're just using this aerial, which is obviously integral to the receiver. And we're going to see we have the transmitter set on its very lowest power. So it really is only less than a watt output. And then we're going to see what it is that we pick up without using this system. And then we're also going to see what it is that we pick up using that system. Okay, so first of all, I'm going to get the transmitter turned on by my assistant, and then we're going to set up here for a comparison experiment. Okay, Rob, you can turn on. Okay, so transmitter is now on. We have 5 bars, 1.86 megacycles, and what I'm going to do is, that's just coming through the aerial. I add myself as the aerial, just to show that that's where it's coming from. Obviously it's going to strengthen the signal slightly as I act as part of that antenna. I'm going to wind the sensitivity down, so we're just down on 2 bars. That's 3, just a little bit further. Okay. Now we'll just check that and turn off and turn on. So back to 2 bars. Okay, so from that point I'm now going to, that is what we are receiving of the sky wave from the transmitter over the 18 meter point to point. That's got nothing to do with the ground system here. This receiver is not connected to the ground, it's just placed here on the bench, and it's using a fully extended aerial. So I've got the aerial from here extending upwards. It's about 1.2 meter aerial extending up to the top here. Okay, so without turning it off, I'm going, well actually, to connect I will. Okay, Rob, and off. I'm going to connect the coil. So we're now connected to a tuned receiver coil in the TMT. The length of the telescopic aerial is correctly set for the 1.86 megacycles that we are receiving when we are connected to the ground system, the external ground system outside lab 2. So this is now a test using this receiver, and of course the sky wave and the ground wave are involved. We're going to have to do that part of the investigation a little bit later in this experiment as well. So let's see now what we get through from this system. Okay, Rob, you can turn on. Okay, so we see that in comparison we now have six bars here. We calibrated it down to 2. That's what the system was just receiving by itself, this receiver. And when we connect it to the Tesla transformer receiver, the part of the TMT system, then we've gone up to 6 bars of 1.86 megacycles, and that will be a combination of the sky wave and the ground wave that are being received by this antenna system. Okay, and off, Rob. And on again. Okay, good. So we're just also going to go back, check our control, make sure we are still setting the right calibration point, and off, Rob. Okay, so if I unplug, go back to just this antenna, and on. Okay, so just coming through the tall vertical antenna of the Sony, we're back to the 2 bars that we originally calibrated. I will also do it in real time. Let's see if I can find it out. Okay, so I put this in. This basically disconnects this aerial and connects the receiver to the BNC here. So that selects which antenna is being used. So we see when I plug it in, there's nothing connected here, and the signal is dropped right off. If I take that out, it's going to be back again. It's receiving through the vertical antenna. Put that back in, signal's gone, and now I'm going to connect the BNC to the edge, and now the signal is back, and we are back up to 6 bars. Okay, so this is now shows that our Tesla coil receiver produces at least a higher gain than this vertical antenna, and that may be for a number of reasons. That may be because it's able to couple more of the skywave, and it also may be because it's able to couple more coming through the ground. So there will undoubtedly be a Telluric channel involved here, or the ground wave, and it will also be picking up some signal through the skywave. And we're going to have a look at a comparison of those two things as we work up into some higher powers. Okay, good. Okay, so I've replaced the Sony receiver with a Hewlett-Packard 435B power meter. It's a precision instrument with a, let me just get the number, 81H power sensor. This is a thermocouple power sensor, so it works on heating of the internal sensor. This is on a system which is connected up to, read up to 3 watts. So we're going to be using this to measure very accurately the power that we've got coming through. So first of all, we're just going to check the calibration. I'm going to 0 the meter, nulls the bridge inside. May have to do it a number of times. And then I'm going to attach the output of the power reference, which is basically a 1 milliwatt, and we are set on the 1 milliwatt range here, and the cows come right over to 1 milliwatt. So our calibration is good. Disconnect that and reconnect that to the input of the experiment. So, and I'm going to go right down to the most sensitive range, read 0. I may have to do that a number of times. Okay, so again at the other end we're still very minimum power, only really just less than a watt that we're putting out of the system, and then we're going to see we've got that now set to its most sensitive range, 300 microwatts. So that's this scale here. Okay, Bob, if you turn on. Okay, so only a very small movement. Rob, turn off. We'll just re-zero at these most sensitive ranges. and turn on. So only reading right at the bottom there at about 25 microwatts being received by this system. Around about 1 watt in and off. And back on. Around about 20 microwatts and off. Okay, so that's just at a very minimum power output, just to check that we are actually receiving something. So now we're going to go up in power a little bit. I'm going to move up in gradual stages, starting from 2 watts. I'm going to put this up a range. Don't want to swamp the meter. We can always turn it down if we need to. Okay, Rob, if you want to set 2 watts and let me know when that's ready. It needs to be, it's very sensitive adjustment at the transmitter. It needs to be set and then just tuned with the antenna tuner as I showed before, just to make sure that everything is in the right place, and then we'll see how much we're getting through. Great, thank you. So 2 watts has been set. We are on the 1 milliwatt range and we are receiving about just over 600 microwatts. 1 milliwatt is full scale deflection. We've gone up to 2 watts and we are receiving about 650, almost 700 now, microwatts. Okay, and off, Rob. We just check the 0 again. Yeah, actually the 0 is quite good. And on. Just being readjusted again. Set it back to as accurately as possible, back to 2 watts. It's a very right at the bottom end of the adjustment of the transceiver at the transmitter. Is that set to 2 watts now, Rob? Okay, so that's 2 watts now, so 500 microwatts. This is 1 milliwatt. At the top here is 500 microwatts. Again, very slight adjustments at the transmitter. Okay, you can turn off again, Rob. And Rob, I want you to turn on this time, but don't adjust any of the settings. Just turn back on again. Okay, so that's back on without adjusting any settings. We're back up to just over 500 microwatts of power. Just to show that there's it's a consistent transmission. And off. Okay, you can turn off, Rob. Okay, good. So let's re-zero again. Alright, so now we're going to go up. I'm going to go for up to 5 watts. So I'm going to turn up this, that's 3 milliwatts, 10 milliwatts range. We can always turn back down again if the movement isn't very much. Okay, Rob, if you want to set to 5 watts, and then let me know when that's tuned and set. Okay, thanks. Okay, so that's 5 watts set and tuned, so I can go down as you go down the range. Maybe even one more. Okay, so over to just over 800 microwatts. We're on the milliwatt range again. So for 5 watts going in at the transmitter, that's measured by the Bird 4391 RF power analyst that we were using before, and we are measuring here now about 860 microwatts. And off. We just we zero our bridge. Okay, you can turn on Rob without adjusting any of the controls again. Okay, so right over 960 microwatts for 5 watts in. And off. We'll just check our tuned position at the receiver, just see if we can improve on that at all. So I'm going to go up a range. Okay, you can turn on Rob and readjust to set for 5 watts to make sure it's tuned. We'll just wait for that to settle while it's being tuned at the transmitter, and then I will come round. Great, thanks. Okay, so that's set. So we've got 5 watts set. Again, we are up at around about, just want to tune again slightly, Rob, just keep it at 5 watts. It's moving around slightly. Okay, so that takes it back up to about 800. Okay, good. So I'm going to make small adjustments to the tuning here. I think we can even use another range, just give us a bit more accuracy. Not a lot of change when I tune, so the tuning is there. Obviously we do get slight drift on the, if I was to put my hand on the coil here, obviously going to damp it all down. There the power goes out. I'm also going to change the tune length. I just changed the length of the antenna slightly. Take it down a bit further, see if there's any, can be tuned any better. Okay, so now it's off tune. Bring it back up. The starting point. Okay, it's the best point of tune. I'll just go the other way. So it's right back down again. So I've made there the tuning area at the top longer. I'm going to reduce it down. So it's increasing the frequency as I reduce it. It's increasing its tune frequency. As I make it longer, it's basically decreasing its tune frequency. Just get that back to where we started. I can measure it as well. I have a defined length, which is accurate tuning. Just do a little bit of fine tuning. That looks about right. I'm just going to measure the length of the antenna, make sure that we actually right back to the optimum position, back at 800 microwatts. Just slightly come away from it. Very fine adjustments. That's it. Back up to around about 800 microwatts. Just check the measured length. Yes, it's back to 57 centimeters, which was our starting point. 800 microwatts. Okay, Rob, you can turn off. We just reset our 0 for the bridge. And back on. Okay, back to the initial setting, 800 microwatts. And off. Okay, you can turn off now, Rob. Okay, so that was at 5 watts. We're going to move up to 10 watts now. I'm just going to read 0. And I'm going to move up a range to 3 milliwatts, full scale deflection. As you can see, we are putting quite a bit of power, a much higher order of magnitude power at the transmitter, and we're only getting small amounts through. We appear to be about the optimum tune point, both for the parallel tuning capacitor here and also for the series modes point with the extension of the aerial at the top end of the secondary. So only a very small proportion of the power that's being put in to the transmitter is actually being received by the receiver here. And now we have to take a look at how much of that is coming through skywave and how much of that is coming through ground wave. So we'll move up to 10 milliwatts at transmit power and just see how that looks in relation to what we first of all get on the meter as is, and then we'll disconnect the ground system, retune and see entirely what we actually just get with the system when it's just used as a skywave antenna without ground reference. Okay, so Rob, you can go to 10 watts. Great, thanks. Okay, so we've got 10 watts at the transmitter, and we are tuning around a little bit. That's reading 110, no, 1.1 milliwatts. So 1.1 milliwatts, 10 watts in, 1.1 milliwatts. Let's just check the zeroing. Okay, Rob, and turn off. Yeah, the zeroing is quite good. And turn on without readjusting. .25. So 1.25 milliwatts for 10 watts in. And off. Okay, so for 10 watts in at the transmitter, we receive 1.25 milliwatts here at the receiver system, both through the combination of the sky and the ground wave. Now what I'm going to do is I'm going to remove the ground system. I'm going to attach a single fly lead. That's a 10 metre single wire, not connected at anything at the other end. So it comes round, down, and it just goes around the lab floor. It's not connected to the ground system outside or to any other ground. Now we have that there to make sure that we lower the impedance at this end. We want to keep it in the same quarter wave mode that it's operating when it's connected to the ground system. We are going to have to retune, because by changing the wire length here, we have effectively changed slightly the series mode frequency of this receiver. So we need to get it back to its optimum receiving point and see how much power we could receive. Now, so in other words, there is no connection to the ground. There is no power from the transmitter coming through the ground wave. We are only connected here with the sky wave based upon the wire length of the secondary coil, and then what is coupled through the same parallel circuit that we had before. So if we turn on, okay, if you want to turn on, Rob, and don't readjust. Okay, so obviously power is very low. The reason it's very low is because the frequency will be tuned slightly differently. So let's go up a range, and we will need to increase the length until we have hit a more optimum position. We'll find where that optimum is. We went up a range. Just to get the sensitivity, I will turn it back to the previous range. Okay, so still going up. Extending. Okay, now we're going back down again. So we went through the optimum tuned frequency. Just going to make small adjustments now until we can hit that tuned frequency, and we've optimised the amount of power that we could couple for the transmitter system. Seems to be around about the optimal position. And now we go back to the same range that we were on. Oh, that's going the wrong way. Back to there. And we now see that we have, I don't want to get too close to the aerial to read that. We have around about 550 microwatts. So 550 microwatts, and we had 1.25 milliwatts when both the ground system and when the ground wave and the sky wave are being received. So when we had the ground system connected, we were at 1.25 milliwatts. Now with the Telluric ground system disconnected just through the sky wave, we are stably reading, I'll get too close to the antenna, that affects it. Its resonant frequency will be affected by my close presence, around about 550 microwatts. I'm just going to come around and check that closely away from, yeah, so around about 500 to 550 microwatts. So that's from just Skywave. Now I'm going to reconnect the ground system. So I'm going to disconnect the single wire at the bottom that was lowering the impedance. I'm going to reconnect without changing anything else. I'm going to reconnect. Obviously I'm going to have to retune because the wire length would have changed. Till I hit an optimum point, the optimum point again, the optimum point of tune. Around about there. I'm just going to check my wire length again, so I've got it right back to where I had expected it to be, slightly down. That was back to where we were before, and if I go read now, we have both the ground wave and the sky wave involved, and we are back at 1.2 to 1.25 milliwatts from 10 watts in from the transmitter. And this is with the Telluric channel connected through the two ground systems and through what is received through the Skywave as an antenna. And so just to recap that, let's measure and see if it's stable. Yes, it's around about just over 1.2 milliwatts, and we had about 550 microwatts, or just over half a milliwatt, when we only had the antenna on its own connected and retuned to be at the same frequency, same series mode frequency. We have to do that because the wire length changes when I take out the ground system. So that basically shows that we are receiving about 650 to 700 microwatts of power through the ground wave through that Telluric system from 10 watts put in at the transmitter. There's really no consideration of the ground, the nature of the soil or the ground between these two buildings. They just both have a ground system. The transmitter has a fairly large ground system, and the receiver here goes through the same grade wire, goes down to a RF earth system was made from a single rod just outside this lab, and that's what we're able to receive stably. Good, okay, so we'll also go up a bit in power now as well and see how this scales as we go upwards. Okay, Rob, you can turn off. Okay, just zero our bridge again. And we'll move up the stage. Take it one more just to be safe. And we're going to go move up to 50 watts. Okay, Rob, you can set 50 watts now and retune and let me know when you're ready. Yes, 50 watts, 50. Great, thanks Rob. Okay, so that was 50 watts set at the transmitter. Let's go back down a range. We've got, that's on 10 milliwatts on the upper scale, so we're reading about 70, not 10 milliwatts, it's about 7 milliwatts. So we're getting 7 milliwatts for 50 watts in. And off. And off. And back on without readjusting. Okay, so there again, so we're now 7.2 milliwatts for 50 watts in. And off. Okay, so we've just now set up, switched over to the linear amplifier. We're going to run up to 100 watts. We're at 50 watts before. At 50 watts we measured just over 7 milliwatts of power. I've moved up now to the 30 milliwatt range. We were on 10 milliwatts before. We'll put 100 watts in at the transmitter and see how much power we can actually get here at the receiver. Okay, Rob, turn on. And just do some tuning. So just adjusting the transmitter. Okay, thanks. Okay, so we are putting 100 watts in at the transmitter, and we are just below 16 milliwatts. So 16 milliwatts out. So 100 watts at the transmitter. We're on the 30 milliwatt range, which is the lower range, and here we're about just over the 16 milliwatt point. Okay, let's just check our zero and off. And on again without readjusting. Okay, so now up to 100 and just over 100 and no, just over 18.5 milliwatts. So 100 watts power in. The tuning is just, do you want to just retune again, Rob? Okay, so we're just resetting back to 100 watts. It tends to, very sensitive, the tuning tends to drift slightly. Okay, good. Okay, so we're back again to 16 milliwatts. So 16 milliwatts of power. Okay, and off. Okay, so I'm going to go up a range to 100 milliwatts, and we're going to move up to 200 watts of power. Okay, Rob, you can go up to 200 watts now and retune, and then let me know when you're ready. So on the 100 milliwatt range, we're just going to set it to 200 watts at the transmitter and retune. Okay, alright, so we are on 100 watt range, 100 milliwatt range, which is the top range, and we're just over 30 milliwatts. So if I turn it back over, it's going to go right over to the far side. So we're now reading about 33 milliwatts, which we've gone up double the power. At 100 watts we had 16 milliwatts, and at 200 watts we've got almost exactly 33 milliwatts. and off, Rob. Okay, we'll just check our 0, which is fine, and back on again without readjusting. .36 milliwatts, and just tune again if you need to. Okay, so that's been readjusted, and we're just back on around about 32 milliwatts, so consistent with previously before. Okay, and off. Okay, I'm going to go up a scale again, up to 300 milliwatts, and we're going to put 500 watts of power in. Okay, Rob, if you want to go up to 500 watts and then retune, and let me know when you're set. Just waiting for that to be set up. We're currently on the 300 milliwatt range, which is the lower one here. Okay, thanks. Okay, so that's now set at 500 watts. It's less than 100 milliwatts, so I'm going to go down a range. And we're back over to, that's a 100 milliwatt range. So now we are on just under, or just over, just let it stabilise, about just over 80 milliwatts at 500 watts. 500 watts in, and almost 81, 82 milliwatts. And off. And on again without readjusting. Okay, back to 80, almost 84, just over 84 milliwatts of power. So 500 watts in at the transmitter, and 80, just over 80 milliwatts, 82, 83 milliwatts at the receiver. Okay, good. Okay, Rob, and off. Okay, so we can see with the combination of the sky wave and the ground wave at the Telluric channel and what's being received through the sky wave, we 500 watts into our ground system, and we are basically receiving around about 80 milliwatts of power. So a very, very large reduction. Point to point, the ground systems are only 18 meters apart. So a lot of power lost, pumped into the ground, and also radiated, which we showed lower at the lower power at about 100 watts. At 10 watts, sorry, we showed that we had about 550 microwatts passing through the sky wave, and we had around about 650 to 700 microwatts passing through the Telluric channel. So a lot of power lost. Obviously that the frequency that we're operating, there's going to be high losses in the Telluric channel, and also large losses in the skywave. We only receive a fraction of what it is that we're actually transmitting. I mean, for a very sensitive radio receiver, that's more than enough for radio, but in terms of transference of electric power, this system is not adequate as it is at this frequency to be able to pass any quantity, reasonable quantity of power, at least through the Telluric channel and the setup that we have here. Tesla worked at a much lower frequency. Obviously, the response of the Earth, the planet at different frequencies makes an enormous difference to how the telluric channel operates. And we're going to be going into that in more detail in the Telluric Transference of Electric Power series that's coming next, and also we're going to be going out in the field, taking this receiver progressively further and further distances away from the lab and looking at some experiments and how it actually works out in the field. Good, okay, so this really completes the second video in transference of electric power, the single wire versus telluric. All the details will be in the write-up. I will put the various input powers and the response powers, and obviously we will have the small signal analysis in there as well, and obviously an assessment, analysis, and some conclusions as to the result of the experiment. Good, okay.